Okay, so next we have Yoshua. Yoshua is a professor at University of Montreal and director of Mila. Now, unless you've been encased in ice for the last number of years and missed it, you know that Yoshua with Jan LeCun and Jeff Hinton won the Turing Award in 2018. Their work on neural nets and deep learning. And among many other things, he's a fellow of the Royal Society of London and Canada and Knight of the Legion of Honor of France. You may not know that he has the highest H index in the world as of last year. So we're really all just living in Yoshua's world. Now, I was lucky enough to start to sort of know Yoshua. It was a smaller field then when he was tenaciously working on neural nets and before he became a demigod. And what I always observed is that he was always particularly good at finding inspirations in other ideas that other people weren't looking at. And so I credit this to at least partly to his success and creativity. So I'm really looking forward to hearing Yoshua's latest ideas. Take it away, Yoshua.
Right. Thanks for the kind words, Alex. Let me see if this works. So, okay, before I start really, I want to give you a bit of perspective of where I'm trying to go. So instead of trying to interpret existing large neural nets, for example, causally, because I'm also going to talk about causality, I'm interested in having neural nets that discover causal explanations for the world, for the data, and can then learn to answer questions about that understanding. And that's essentially the essence of model-based machine learning, where you separate the discovery of knowledge, which is like the world model, from the inference. And the kind of world model I think we need for robust out-of-distribution generalization is a causal one. And then coming to conclusions, answering questions, that's inference, that's reasoning. And I will argue that this is a promising path for eventually building AI systems that can act like scientists, in the sense that they try to understand the world and not necessarily act in it, because I'm very concerned about AI safety. If you've been following some of the discussions in the last few months, you can also check my blog, where I have a lot of posts about the safety questions, if you want to learn more, because I won't have much time today. So yeah, maybe a good starting point is, what is missing from the current approaches, like ChatGPT and the other chatbots that have been putting out, that they're all more or less following the same recipe. I think many people in this summer school will agree that these systems are weak in terms of reasoning and, of course, truthfulness. And it would be nice if we could make them better understand causality, including how to discover causal structure that is not already known. A lot of the work in causality, in science and in AI has been about taking advantage of existing knowledge, causal knowledge. But here I'm asking, well, if you're a child or if you're a scientist and you actually have to discover the causal structure, what can be done? And of course, one of the objectives is that these kinds of models would be more amenable to interpretation, to provide explanations, to point to sources of evidence, and so on, which we want for many reasons. But maybe more fundamentally, they might help to generalize better out of distribution, as I'll try to explain why, and to require less data for training compared to these huge models. So one little parenthesis first is that these large language models are not even estimating the kinds of probabilities that I think we should be thinking about when we think about reasoning and probabilistic notions of truth. So what we really should be caring about is not the probability of observing a particular word sequence, that expresses some statement, but rather the probability that that statement is true, which numerically is a very, very different object and very different number. So for example, the probability that the newborn is female, let's say, and we haven't seen yet, is true, should be something like 50%. But the probability of generating the words or seeing the words in a text that says the newborn is a female, well, that probability is much, much smaller. And there are many other sentences that mean the same thing. So it's just the wrong quantity. Okay. The other maybe more important angle I want to bring forward is inspiration from humans. How do humans reason? There's a lot of information to be gathered from cognitive neuroscience, from neuroscience, and the way I like to think about this, all this work is that what humans are doing when they reason is inference. They are applying pieces of knowledge that they know. They're composing just the right pieces. And in fact, not all of the pieces that could be relevant, but only a very small subset that comes to your mind, to your conscious mind, in order to explain something, plan, imagine, learn, and so on. So first of all, there's the notion of how does our brain break down knowledge into these composable pieces, and how do we select those pieces? And the part about selecting those pieces is very much connected to what's called the global workspace theory in neuroscience of consciousness. So you can think in this theory of thought as a highly, very few bits, something like a short sentence, very few concepts that are related to each other. And we're going to have, of course, a sequence of these thoughts forming what people now call a train of thoughts. But even that sequence is very few bits, and it's an incomplete description of the state of the world, or what might unfold in a plan, or an explanation for some data. But yet it's a well-selected set of bits that are very informative about whatever the thought is about. Also, another property of what's going on when you become conscious is that it's highly stochastic. For example, the Necker cube that you see on the right, you could see it in two ways. So, your mind can interpret it in two ways, and it's more or less 50% for normal people, at least. It's completely random which one you're going to see, but then a few seconds later, you might switch to the other. So there's clearly, and we can see in measurements in the brain, this randomness play out. And by the way, there's also some evidence that that inference is Bayesian, again from experiments with humans and even animals in terms of the kinds of inferences that they're making. Okay, there are a lot of let's say priors or desiderata for human-like reasoning that I think we're not exploiting in machine learning, and that we could. A large part of what we do in machine learning is coming up with inductive biases. In other words, ways to constrain our learners that will make them generalize better. So I won't have time to go through this whole list because I have 2 pages here. But one aspect I want to talk about today is the separation between a world model and inference, which is not the way current state of the art the neural nets are trained. I already mentioned the notion of learning a distribution over statements that are true or false, like sentences in a thought. The fact that we have to deal with possibility so if you think of these statements as random variables, there's an exponential number of them. Because how many 5-word sentences can you construct? A huge number. And yet we're going to be focusing on just a few at a time. This bottleneck of what goes through your conscious working memory has implications in terms of machine learning as a form of sparsity of the dependencies that exist between those random variables and between those statements. Also, of course, for humans, how the world works is not something that we're born with, and there may be a lot of possible explanations. So that's where the Bayesian part comes in that I'll mention. Yeah, I'll move on. So let me say a few words, especially about causality, which is another of these inductive biases in my list. So I like to frame a causal model in the language of traditional probabilistic models. And I believe this can be done if you, in addition to the normal random variables, I call them V here, you introduce another set of random variables that are like special random variables that are the intervention. So for each random variable, there's an intervention that you could do that will change this variable. And what's interesting about a causal model is that whereas how it differs from a regular distribution over the V's, the regular variables, is that we now have all the possible interventions and for each intervention, there's an exponential number of possible interventions if they were discrete. For each possible intervention, there's going to be a different distribution over the random variables. So really, a causal model is a family of distributions over these random variables indexed by the interventions. So depending on which variable are intervened with what value, you get a different distribution. So you've got a family of distributions. Now, okay, so we have all of these distributions, but how does that help us? Well, the assumption in causal modeling is that all of these distributions share the same parameters because it's the same parameter, the same causal mechanisms, but it's just that we change this variable, and so it changes the consequences of that, and you get a different joint distribution over all the variables. Now, this is really important to understand because this is what gives causal models, if we are able to learn them, the power to generalize to distributions you've never seen, but corresponding to interventions you've never seen. So we maybe see one intervention, like no intervention at all, or a few of them. People do experiments. And from that, really what we aim at is learning the causal model that now allows us to make inferences about other distributions that correspond to new interventions. Maybe interventions we don't see. Sometimes the intervention variables I are unseen, and we make inferences about I themselves. And humans do that all the time. We observe some changes, and then we are asking, what happened? Well, that's exactly what we're doing. Okay, so the effect of changing the intervention variables is what's called intervention surgery, like setting the value of a variable, and that disconnects it from its parents, its causal parents. And once you frame this like this, causal inference is just probabilistic inference, and it will do reasoning for you as well. In other words, given some information, you can answer questions about other things. Now, once you start thinking this way, you see causality is really a special kind of inductive bias. And usually it comes with additional inductive biases like the sparsity I mentioned. Like usually we think of a causal explanation, a causal graph involving a very few edges that connect the variables together. Now, there is an issue with causality, which is that even if we had an infinite amount of data, but just of no intervention or a single intervention, unfortunately, we would not be able to learn what the correct causal structure is. What's the causal graph that links directly causes and their direct effects. So this is well known, and the set of graphs that correspond to an infinite data set that are consistent with that data set is called the Markov equivalence class. So there is going to be ambiguity about what the right causal theory for the data is. In addition, of course, we don't get infinite data, we get finite data. So what I've been talking about in the last year, more or less, is, well, instead of trying to find a single graph, which is not going to be the right one anyways, or even trying to find this class, which might be exponentially large, of the Markov equivalence class, why don't we just bite the bullet and go Bayesian and learn the posterior distribution over the causal explanations, causal graphs, and causal latent variables, given the data. So in that way, we absorb all the sources of ambiguity, and in theory, the right way of answering this problem. So I talked about the graph, but really there are other things we don't know, like we don't know the parameters of the causal mechanisms, how a variable is influenced by its parents, its causal parents, and often we don't observe all the causal variables. Maybe there are some we observe sometimes, others we don't, and we may have to discover causal variables that we don't directly observe as well. That's called causal discovery and causal representation learning. But it turns out that the posterior distribution over all the things we don't know, so the causal graph, the parameters of the mechanisms and the latents, given everything we know, which is observed, is a quantity that we actually can compute up to a normalization. This is the thing on the right, which is like a product of priors and likelihood terms. So we can actually compute that posterior up to normalization. The thing we don't know how to do is sample from it and also marginalize over the things we don't know if we need to answer questions, which is really inference. So a lot of the rest of my talk will be about trying to answer that. So we need machinery to perform general purpose inference, like given some random variables x, trying to sample other variables y, having some kind of knowledge of how y and x are related through an unnormalized joint distribution, which is what we have in this line. So we can compute the unnormalized joints of the things we care about, but we want now to be able to do inference. And the challenge is the y here is not like a class. Y here is many random variables. They could be discrete, continuous, and they maybe the biggest challenge is that this y that we want to do inference over could be highly multimodal. In other words, given a value of x, there's many different kinds of values of y that could be very different from each other. That are all like good answers, but different answers. Also, y could be a complicated object like a graph, for example, in causal graph. So one of the things we've been exploring in the last 2.5 years are these generative flow networks, so G-flow nets, that I'll say a little bit about, where we're going to learn to sample the y given x as through a sequence of stochastic steps. So learning to represent and sample from a very complicated multimodal distribution is difficult. Like how do you parameterize that? But if we decompose that generation in a sequence of steps, like in autoregressive generation or in diffusion models or in these G-flow nets, then we can represent very rich distributions. The other thing that's nice about the approach I'm going to talk about is we may benefit from the generalization power of machine learning, so that even if the number of modes of the variable y is huge, and we don't get to see all of the high probability configurations of x and y during training, we may be able to use things like neural nets, that machine learning in general, to perform what's called amortized inference, where we learn to perform the task we want, like sampling and marginalization, in a way that implicitly is trying to capture all the modes without actually having to see all of them, because we can generalize from the modes we've seen, from the configurations that are probable, to unseen ones, because there is structure in the distribution. If the distribution was random, then we wouldn't do any better than MCMC. But MCMC is typically not using machine learning, and so it just has to explore everything. Whereas if you learn, you're able to generalize to things you've never seen without having to actually be shown those things. So G-flow nets are related to MCMC methods. They're also more related to variational inference methods. And they differ from the traditional variational inference in that they use a different training objective, which is not the elbow, the KL divergence that people love and use, but something different that has a nice advantage in terms of the diversity of the samples that you get out of this, because you can train them in a way that's called off policy, which I won't have time to explain, but is well described in this paper that came out at the last iClear, called G-flow nets and variational inference, and that I encourage you to look at. Let me say a few words about how we can train these G-flow nets to actually perform both sampling and marginalization. So marginalization is performing a sum, like the first equation here, where the number of terms in the sum, why it could be difficult is that the number of terms in the sum could be exponentially large. So we can't actually compute that sum explicitly, otherwise we would just do it. But we need to estimate that sum without having to run through all the XY configuration, actually all the Y configurations. So here we're interested in conditional distributions like Y given X. And so given an X, we'd like to have a sum over all the Ys of some given unnormalized distribution R of XY, like the Bayesian posterior that I talked about. So we are interested in this object pi of Y given X as well. That's the sampler that samples Y given X. And it's just the R, which I use R for reward function, which is really a normalized probability joint, normalized by S, which is the normalization constant. I mean, it's a function of X. So we'd like to learn these two objects. And if you take the second equation and you just, move S to the left-hand side, you get a constraint, an equation on the third line that says pi of Y given X times S of X should be equal to R of XY for every XY. So we know R, and we are trying to learn S and pi. And it turns out that you can define the loss function like the fourth line, which is just trying to make the thing equal by minimizing a discrepancy. It turns out that when you're minimizing that loss function in average, so that you're pushing down on all the XY pairs, then you recover that constraint and you end up with an estimator of both the sampler and the marginalization. So this is a simplified view of what is going on in GFlowNet's training, but I think it helps to understand why they can do both of these things. So we've been applying this to causal graph discovery. So we have this paper that came out last year and a series of other follow-up papers, which you should be able to find easily. This whole project has been led, the project with causal discovery with GFlowNets has been led by Tristan Deleu, the first author of that paper. And so this one came out at UAI last summer. So the gist of it is the GFlowNet is going to sequentially construct a graph and then sequentially construct values of parameters or values of latent variables. For example, for the graph, you see a set of possibilities here. It's like we start with an empty graph and then we add an edge and then another edge and so on. And at some point we decide, okay, I think the learner, the sampler has a special action that says, I'm done. And it outputs a graph. And you learn that sampler that as a policy that if you minimize the training objective will give you the right posterior. Okay. So as I said at the beginning, I'm interested in applying these ideas for inference in the context where we're not starting from a neural net that's been trained in the traditional end-to-end way, but we're trying to learn both a model of how things work, which would be a causal model, a Bayesian causal model, and inference machinery. So something you need to know about model-based approaches, like in model-based reinforcement learning, for example, is that when you have a model, you can basically consider it like a simulator, and using it, you can train an inference machine that answers questions without having to refer to the real world or to the data. And so the size of your inference machine is not limited by the amount of data. You can have a neural net that answers questions, which is at the end of the day what we typically want to make inference. And the size of that neural net, it could be as large as you want. It's only limited by how much compute you're willing to put in. Whereas the size of the model that captures the causal structure is, of course, something that should be very much influenced by the amount and richness of the data. But the way we're training current neural nets is different. We just train, this one neural net that implicitly learns about how things work and also performs inference. The problem with that is typically the size of the model that's needed to explain how things work, like the actual, think of like the laws of physics or the rules of the game of Go, the underlying world model is typically going to be very small. Like you only have like 9 rules in Go, and physics is just a few equations, right? it's inference that's expensive. In other words, typically your inference machine is going to be a huge neural net, whereas your model, in terms of number of bits, should be something very small. If you confound these two things, then you're going to end up with a world model that is too large. And in a way, implicitly, you're like overfitting your knowledge of how things work. And your inference machine is going to be too small because you also want to avoid overfitting. So you're going to make it smaller than you should or train it less than you should. And so you're underfitting in terms of inference. And of course, if we separate model and inference, now we can also introduce inductive biases like causality and prior knowledge that we may have about a domain, coming from humans that are going to help with interpretability and all these things. So that's the approach we've started working with. We're still in the early steps, but the longer term objective is to develop AI systems that play the role of a scientist. In other words, the world model part is like trying to find new laws, new regularities that are really part of the causal explanation for how things work. And that could actually help human scientists to figure out these answers. So really, it's like having a peer scientist in the future that help us figure out, just like a pure scientist would, how things work. And such a system wouldn't need to have goals. It wouldn't need to act in the world. I think we should have humans in the loop when we're not sure. That's important from an AI safety perspective. I'm working on trying to prove that under what conditions this kind of setup guarantees that you will not lose control in the sense of AI safety, in the sense that the machine will not start trying to sneak on you and become self-preserving, have its own goals that do not correspond to your own goals. We're not there, but I think this is an important direction to think about in terms not just of improving the abilities of our system to generalize better, to reason better, to be better in tune with how humans express and understand knowledge, but also to be safer and protect humanity rather than destroy it. So on this, I'll be happy to answer questions.
Okay, awesome. Thank you, Yoshua. Excellent stuff. So while people are working up the courage to post a question, let's ask a few. So just a clarification. So your world model, if I understand it right, is or the output is a probabilistic graphical model.
It's a distribution over graphical models. So a GFlow net is a neural net. What it outputs is, if you want a program or a causal graph or a set of parameters that corresponds to a world model. So what we get at the end is not one world model, but a Bayesian posterior over world models. And so then you might ask, what do I do with that? Because I don't have a single model, I've got an infinite number of them. Well, you train another neural net. Actually, it's the same, but you can think of it as a separate thing that does the marginalization part, which is basically question answering. So question answering that is consistent with the world model. And question answering is the thing you can use, right? That's like ChatGPT or something, or whatever in a particular scientific application.
Oh, okay. So far in most of our presentations in this meeting, people have assumed some kind of symbolic resource.
Well, what's symbolic here is the causal model, right?
Yeah.
So the data structures that describe how the world works, you can think of like equations in physics, right? So these are symbolic. Now, there may be numbers there, like in an equation, you can have numbers. But essentially, the whole thing, should be very compact. And the analogy would be like the way humans come up with theories. We come up with equations, we come up with concepts, new variables that don't exist in the real world, but that help us abstract how things work.
So you get that as an output, or can you also put in some of
as
those?
an output? So you should think of it like it's outputting theories.
Mhm.
And those theories can be kind of checked against the data, and that's how you get the score, which is the unnormalized joint probability.
And do you also allow sort of people to come with prior knowledge?
Yes, yes. You can easily constrain the generation so that it's going to be constrained. So, for example, we've used this a lot in chemistry, a lot of the work, where we know a lot about the laws of chemistry and what makes sense and what doesn't make sense. That can be used to constrain the actions to generate those theories about molecules, for example.
Here's a comment. Yes, so given intelligence as we know it, it's been observed in social animals. Could causal graph discovery and OOD generalization be an emerging quality of a requirement to communicate to other agents by maximizing information per chunk of transmission? For example, we
Totally.
can consider
Totally.
a knowledge distillation as a form of communication.
Yeah, totally. So the way I think about a world model is exactly as a compression of knowledge. And if you look at the Bayesian posterior, it does exactly that. So if the prior is like e to the minus length of the theory, like the program or the causal graph or whatever, then this will exponentially favor small size models that also fit the data. So what we do at the end, really what's going on is we've got this neural net that learns to generate compressed theories that explain as much data as possible, which I think is what machine learning should be about.
Is the model run in a simulation within which a neural net agent lives inside the model and responds to queries coming from the outside?
So one of my students has been investigating the application of these ideas in reinforcement learning, but for the most part, we've been more focusing on just given a data set, how do you come up with, say, causal explanations or a model of that data? But there's actually a subset of the applications of these methods in active learning, where once you have a Bayesian model, then you can use it to help you decide what experiment you should be doing next in order to minimize the epistemic uncertainty about the world that the model currently entertains, according to the Bayesian posterior.
Now, my own question. So, of course, that's notoriously hard, learning causality from
Yes,
just raw data or static data with no actual
that's right.
action.
That's why we're also investigating the case where the learner can propose interventions, which are experiments. Yes.
Are inference capabilities sufficient? Correct or intermediate hypotheses are key to most non-trivial goals. Usually they come from intuition / flashes. How
Yes.
can these be generated?
Well, that's exactly the objective here, is to train this generative neural net that produces those flashes of insight and those theories. Now, there's a part that I didn't talk about in my presentation because this is still like an open problem, really. We don't even know how to do it mathematically or algorithmically, which is the way humans generate hypotheses isn't that we generate a full theory of everything. We just have these little pieces that come because we have this bottleneck of conscious processing. And it's not clear yet how to do that, but humans do that, and it allows us to be extremely efficient about learning how to generate good theories by small pieces, rather than the way we typically think of it in machine learning, where you lay out the full set of parameters of a model, for example.
This is maybe similar to what Les Valiant was saying.
Alex, Francesca, I have a question. So, Francesca, you can unmute yourself.
Oh, go ahead,
Thank
Francesca.
you. No, because for some reason I cannot send it to the here. So I was wondering, is this method focused on language? Like,
No.
or does it work with any, or is it inherently
Any random variables. It's just generic probabilistic inference that we're after here.
Okay,
So it could be used for a language. I just use the language example because people are obsessed with LLMs these days.
Yeah.
And I just wanted to point out that we are not learning the right probabilistic model.
Okay, but
Okay,
does
we'll
it help? Do you think it helps that we have already systems that are building at least some model of the human language, where
Sure. I mean, I don't think those models. I mean, I don't know. I don't know what's going to happen in the future, but I think they're missing some. They're wrong in some ways, but they teach us several important lessons. And maybe the most important, as far as this project is concerned, is they teach us that a very large neural net trained on huge quantities of data can learn very complicated distributions that seem like daunting otherwise. And so what I'm proposing is, in a way, a different training objective, where instead of directly fitting the data, they're trying to come up with theories that explain it. That's the
I
difference.
have another question actually now that I didn't write. So is this approach, do you think it will help also to achieve, or how it can help to achieve some form of value alignment for these systems?
Wow, this is a great question.
Let's keep it for the panel, maybe.
Yeah, that's sure, we can do that.
Okay, good segue, Francesca. So, all right. So now let's move to the panel. So,
Let me restart recording.
okay.